All right, thanks, Sean. So I thought the way I would try to tell this story is by telling a story in terms of how our sort of research evolved here. So I did my PhD with Muriel in information theory, then I went on to do a postdoc in neuroscience. And when I first began to take a look at the field of brain-machine interfaces and what people were doing, it seemed as if people were primarily using neuroscience insights and not much beyond that. And the way I'm trying to tell the story is in terms of a painting or a drawing you're trying to make, and you have to take these different disciplines to integrate them together to make a better painting. So if we start off with just one paintbrush being neuroscience, the types of things that people were doing is, take a look at this picture right here is my postdoc Ray, and he's got an EEG cap on his head, and basically this cap has a little electrodes, little sensors at different locations on the head, and what you can do is that you can control things just by thinking. So for a very simple example right here, when I imagine squeezing my left hand versus imagine squeezing my right hand, the electrical signals on the surface of my head, their patterns change. Very basic neuroscience understanding. So you can basically take that in the high-level framework that people have for these systems is you have a brain, you record some signals, and you do a very basic decision algorithm. So for this example, you could do a very simple classifier and you move the ball to the right as compared to the left based upon the signals that you got. And so, but hopefully what you get from that is, that's not that interesting. It's somewhat of a boring sort of painting. And so what I realized is that perhaps what we need to do in addition is to use some applied math. And if we use applied math and integrate these two together, we can begin to make, better paintings. And so with that, the epiphany that we had, if you think about these brain-machine interfaces, what people were not explicitly taking into consideration is that just like when I'm interacting with this system, it's really two agents cooperating to achieve a common goal. You have the user over here and you have some computerized algorithm. It's not a one-time step deal. It is true that I get neural signals and I need to interpret them, but then I can provide visual or sensory or any type of feedback to the user and they can interact, right? Right, just like when I'm driving my car, even if my car has a misalignment problem, I can still provide a corrective turn to the steering wheel to steer things. So this car is going to have a misalignment problem because neural signals that we get are noisy reflections of the brain state you care about. But if you provide the right type of feedback, then you can provide corrective signals and you can do more sophisticated things. So if you look at this diagram, you can start to abstract things where you can imagine there's something that I care about that's in the user's head. This gets manifested in the aspects of the brain states that I can record from, right? So for example, I might ask you a question, is it to the left of this number, is it to the right of this number? And then you might respond by imagining left or imagining right. So X basically represents imagine left or imagine right, but that's not really what I care about. What I care about is this number that's in your head. So X is a function of what we care about and in response to the feedback we give you. It's like the steering, right? Then this goes through some type of noisy transformation as manifested by the neural signals we collect, and ultimately we want to form beliefs about the information in your brain. And so this begins to kind of feel like a communication problem, right? One of the key things here though is that in a lot of these situations with brain-machine interfaces, the stuff that we care about is inherently continuous, right? So we want to begin to think about, okay, what does it mean to think about what's good and what's bad? Can we develop measures for what's good and what's bad? And if we think about it, imagine that all the things that are in your head that we care about, these numbers, let's say between the 0 and 1 line, or as you'll see, these different paths that you might want to drive a car or something, we can put something like a uniform prior over them, right? And as we collect more and more observations, as Prashant and Ramon talked about, we're going to update our posterior belief. So pi n basically represents my belief on the information in your brain given the observations I've seen so far. And if that starts to concentrate around the W that we care about, then that's good. And if it doesn't, then that's bad. So green check mark or a red X. And it turns out that this basically boils down to asking the question, is the information collected from my observations, does it also signal what's of interest, right? So it's really a question about these two sigma algebras. If the sigma algebra generated by all my observations, this is the information that our EEG system is getting, right? Does that give us the information about what we care about, right? If these two sigma algebras are equivalent, then that's green. If they're not equivalent, then it's red. So you can show this more didactically, but I won't do it here. So what we then began to explore, go ahead, Prashant.
I'm just trying to understand. So XI, YIs, they're all signals in the brain?
X is something you imagine. So you remember when Ray imagined squeezing his right hand or his left hand? That's like the steering wheel command. So imagine it's like you're drunk driving, right? And so the steering wheel command you want to get, the car gets a noisy version of that, right? So X is the feedback signal that you're getting. We're not getting that exactly though. So this is a imagine left or imagine right binary. Y represents the voltage on the surface of the cap. So the 64 voltages on the surface of the cap after you imagine, right? So is that clear? So Y is literally what we collect, right? And traditionally what people were doing is they were trying to figure out what X was. But in some sense what you really care about is the high level goal, right? X is really just a control command, just like the input to the channel. No, I think what drunk means is the noisy channel between here and here. So even if someone's sober, right, the EEG signal that we get is a noisy reflection of the latent command, right? So, right. We're trying to have some fun here, right? Trying to have some fun. So, give him beer. So, what I'll sort of define right here is perhaps a class of encoding schemes, right? So the whole name of the game is that we're going to learn is we have to figure out what's the right next question to ask. It's almost like 20 questions, right? It's like you got a number between 1 and 20 in your head, right? And I get to ask you a question. Is it less than or greater than this number? If there were no noise and I heard you exactly, the first question I'd ask you is it less than or greater than 10? So Q basically represents that question that I'm asking you, this feedback that I'm giving you. What's tricky here is now there's noise, right? So we're doing 20 questions, right, with noise, and moreover, it's not a number between 1 and 20, but rather it's a number in a continuum, right? So those are the two key differences. So I'll define a class of encoders that we can construct that relate to this. And so what we'll do is we'll construct these latent variables, these W tildes, and the way I'll start these off is W tilde 1 equals W. So this is what's in your head that we care about. And W tilde at time I is going to be a function of W tilde at time I minus 1. So the W tilde lies in the same space as the stuff that's in your head in a continuum, right? And there's some transformation of that's modulated by the most recent channel output. And these W tildes are intimately related to these queries. And for the purpose that you hear about conceptually, they're in some sense the same thing, excuse me. And one of the things that we want to focus upon are when this map right here for any Y is actually an invertible map. And because in some sense what that'll mean then is that, so if you take a look at right here, W tilde is in some sense the same thing as X. It's your command. I want to make sure that the next thing that you're giving me sort of is informative, right? As given by this being an invertible function. So if we focus on classes that have this structure, reversible and time invariant, and you see why it's time invariant because this is the same map S. It's only modulated by the most recent Y and the most recent W, but otherwise it's time invariant, right? And it's reversible because S is invertible. Okay, so one of the statements that we can rank right now is we can develop an equivalent criterion for what reliability means. So the left-hand side, remember, this is all the information collected by our computer. And now I'm saying that reliability is equivalent to this sort of tail sigma algebra right here. And the reason that this holds is, okay, remember, the original question of asking about reliability was the information that the EEG system got, is that enough information to collect to actually construct W? This is where we were, but I argue that this is equivalent to doing the following, okay? Suppose that I had the W tildes from time 5 all the way upward, right? And I had all the Y's. I argue I can reconstruct W. And the argument is simply because that map is invertible. So if I have all the Y's, right, and I have W tilde 2, I can go backward to get W tilde 1, right? Or if I have W tilde n, I can go back to get W tilde n minus 1. So if I have all these W tilde i's and I have the Y's, I can reconstruct W. Moreover, it goes the other direction as well. It's basically because the map S is invertible. These two sigma algebras are exactly the same thing. So when I take the intersection, this holds for any I, all right? Therefore, it holds when I take the intersection, all right? So I'm taking an intermediate step right here, and bear with me for a moment. And so what we now have is the question of reliability is the question if this information generated by the Y's is equivalent to something related to a tail sigma algebra. Okay, and why do we want to do this? Well, hopefully Ramon will like this, because now what we can say is that for any RTI encoder where those S's are invertible, now the question of reliability, I argue, boils down to asking about this auxiliary process, whether or not it's ergodic. So it's a yes or no question. Is this process ergodic? Then you get reliability. If it's not ergodic, you don't. Okay, and what does ergodic mean? What ergodic means, right, is that the tail sigma algebra, which is this intersection right here, is this trivial, right? Meaning that every element of the sigma algebra has probability either 0 or 1. Right? Okay, so the proof of this is that, first of all, from the previous slide, any RTI encoder, if I take the sigma algebra generated by W and all the Y's, right?
Sorry,
it's equivalent to this.
Sorry,
go ahead.
Something I probably missed. RTI, does this stand for recursive time invariant?
Reversible time invariant. So the R is reversible. Yeah. Right. Invertible function. So it could have an ITI, invertible, reversible, either way. Okay, so so this we already had from the previous slide. So bear with me for just a minute here. I'm doing this, this relates very intimately to a lot of work that Ramon has done. So first of all, here's what I'm going to argue. All these W's and these X's, they lie in well-behaved spaces, right? So they're what's called countably generated, right? And so what this means that if I take a look at, so now let's imagine for a minute that I condition upon all the Y's, right? If I condition upon all the Y's, then I can construct a regular version of this conditional distribution. And this is stolen exactly from some of Ramon's papers, right? He uses this notation right here, right? So now what I'm doing is I'm looking within the space where I've conditioned upon all the Y's, right? If I've conditioned upon all the Y's, having W1 is equivalent to having W2 or W3 or any of them because the maps are invertible given the Y's, right? And so that's all I'm saying right here is the sigma algebra generated by W is equivalent to having the sigma algebra generated by W2, W3, any of these guys, right? Which is equivalent to taking this intersection within the space. This holds almost surely with respect to the conditional distribution where now all the Y's are fixed. Because if you remember, Wi is Sy of Wi minus 1. So if I have all the Y's and S is invertible, these sigma algebras are the same thing. Okay? And so what's nice about this is that from the perspective of this measure, now the tail sigma algebra is countably generated. And typically that's not the case, and Ramon has demonstrated this very interestingly in some of his recent papers. And so, so now with respect to this measure, this tail sigma algebra is countably generated. So now, if we stand back for a second, let's now re-explore the information generated by the message and all the Y's. That's equivalent to this tail sigma algebra, right? That's just equation star. But now, because of this intermediate statement that I've made, we can invoke this paper by this guy Weizsäcker in 1983 that says that you can re-express this tail sigma algebra as the join of these two sigma algebras, which is the information collected by Y and the tail. And the nice thing now is now I'm basically done because look, the left-hand side is the information that includes W and all the Y's. The right-hand side, now I've isolated the information that the EEG system got joining with this other tail sigma algebra. So it's well known that if this tail is trivial, then you can erase this right here. So what I've done now is I've now boiled down the question to asking whether or not I can erase this tail right here. And whether or not I can erase this tail is exactly asking the question about ergodicity. Right, and so that's the whole statement of the theorem. So now what we have is we have a statement about any of these systems where this S map is invertible. The original question about comparing the information generated by all the Y's and generating all the Y's and the message is equivalent, to this question right here. And once we get to here, that's just a question about ergodicity. So, you happy, Ramon? What part? Is it this intermediate step you don't like? So clearly you buy that this is countably generated if this is a well-behaved space, right? These guys are all the same thing with respect to this measure right here because I've conditioned upon all the Y's.
Yes, but there are uncountably many found sets. So I will write out a little example.
Yeah. Well, we'll go back to this.
Why don't you move on? I will convince myself.
So what the statement that we have right now, what I find interesting is asking whether or not reliability holds is equivalent to asking the question about ergodicity, right? So for any of these classes of systems, it's just this one question right here. So now what we can do is we can move on to ask the question, okay, so now we figured out whether or not these systems are reliable by asking whether or not is this process ergodic, but we want to in addition see can they zoom in very fast. And so zooming in very fast we know is equivalent to trying to maximize mutual information. And we know to maximize information from what's in the user's head to all the observations when we have feedback, there's two key things that we need that Claude Shannon told us. Each sort of command that you gave us should be should be drawn according to an optimal distribution. And moreover, the next thing you tell us should be independent of everything we've seen so far. And so with that, I can just define a class of posterior matching schemes, which are a class of those, structured encoders that I did before that have one extra property, right? Not only do you have this reversible sort of effect, but I also want them to map certain distributions to the other ones. And what I mean by this notation is that this map S better have the property that if the input was drawn according to the posterior, then the output is statistically independent of what you've seen so far. So it's drawn just according to PW. And moreover, mapping this to the X, this should be drawn according to the optimal distribution. Okay, and so if this posterior distribution has a density associated with it, it turns out this is equivalent to asking a basic Jacobian equation right here. Okay, and so what we really need is this map needs to basically be transforming distributions to other distributions in a very structured way, right here. And one example of this is imagine that this was uniform over the 0, 1 line. So FW evaluated at any point is just 1, then what I'm really saying is that the structure of the map should be such that its derivative matches the posterior belief at any point W. And so if I integrate both sides, then actually what I recover is the posterior matching scheme by Shavitz and Fader. Right, so what I'm trying to say right here is that the posterior matching scheme from Shavitz and Fader can be interpreted from this perspective in the special case. Okay, so what can we do with this that's interesting? Well, it turns out what we can do is we can map basically, so we're going to start off with a posterior belief on the 0, 1 line, and we're going to transform this. And suppose now that I can transform every point on the 0, 1 line to a smooth path in 2 dimensions, where 0 is a very aggressive counterclockwise bank and 1 is a very aggressive clockwise bank. Then what we end up doing with this system is what we end up asking the user to do right here. The idea is that this gray path is what's in the user's head. Okay, and so and what we do is we keep querying him. So this path that's partially black and partially red is the query point, and what he signals back, just like when you're driving your car, is he basically looks at the first location where the 2 paths differ, and if it's clockwise, he imagines squeezing his right hand. If it's counterclockwise, he imagines squeezing his left hand. And it turns out that's equivalent to doing posterior matching. It's optimal and it achieves capacity. Oh, excuse me. And so then what we can do with this is we had some fun with our students, and we can have fun games with Google Maps. So you can imagine here you're in San Diego, right, and you're trying to take a path over to Boston. And so what this represents right here is the query, and you take a look at the path that you want to go, and you look at the first location where they differ, which is right here. It goes in a counterclockwise orientation, so you imagine squeezing your right hand. Then we get that EEG, we update our posterior belief, and we re-ask you another question, and et cetera, and eventually we sort of get to here, right? And this is the idea. Okay?
I see you pass to Urbana.
Yeah, close, nearby, yeah. So.
How do you decide what rate you keep moving?
Say it again?
How do you decide what rate you keep moving? So what you're showing here is the overall.
Yeah, so really, the way we interpret this is that this is an infinite path, right? But we're only demonstrating is subpaths for which you have a lot of probability. So what ends up happening with your software is more and more of the path will come as we zoom in more and more. All right, so we're only drawing subpaths for which the posterior probability is sufficiently large. So it's software in the background, right? But really we interpret these as sort of infinite paths. So then we went one step further when I was at Illinois and collaborating with some folks in aerospace engineering, and we were able to actually fly an airplane over the cornfields of Illinois with exactly this paradigm, right? Because the idea is that if you notice the 2 paths, they are together early on and they diverge later and later with time. So what this sort of represents right here, the path that's partially blue with the white dots, this is the path that was in the head, and the blue is the path that actually the remote controlled airplane actually flew, that had a motion planning algorithm on it. And here's just a very simple video to kind of see it, right? So here's the guy. You see, he's not doing anything with his hands. He's this is all just with his motor imagery, and the plane is flying, and it's actually doing this very simple little alphabetization scheme as it's flying over the cornfields of Illinois. So we're not suggesting that you want to do this, right? We're just suggesting that maybe you could do things that you didn't think you could at first glance by exploiting the use of feedback appropriately. And so, but in many situations, the uncertainty that's in our head might not be specific to the 0, 1 line. And so this got us interested in trying to revisit this Jacobian equation because this equation actually holds in an arbitrary dimension, need not be the 0, 1 line. And so it turns out that we can now start to make a connection with the theory of optimal transport to actually construct maps that satisfy this equation in an arbitrary dimension. And the high-level idea, as I mentioned before, is imagine if W is drawn according to P, and I have this map SY that's going to construct a new random variable Z. And the high-level idea is I know what P is. This is my posterior distribution, and Q is the target distribution I want to go to next. So Claude Shannon basically is giving me Q, and P came from my observations. And I want to build a map that satisfies, that pushes P to Q. And yeah, and as I mentioned before, this is our posterior distribution given our, this is a belief that we get from our belief that we get from the output of the EEG machine, and we know that the next thing you tell me should be independent of everything I've seen so far. That's what Claude Shannon told me, right? So it's beautiful. I know what P is and I know what Q is. I just need to figure out the map that pushes P to Q, all right? And basically what we showed just this year is that basically if the channel likelihood is discrete or if it's log concave in X, right, then finding this map is easy, meaning that it's a convex optimization problem and you can literally just code it up in MATLAB. And if we think about most likelihoods like Gaussian, Poisson, blah, 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 most likelihoods actually are log concave, all the exponential families, et cetera, et cetera. So for a very rich class of channel models, trying to find this map that pushes P to Q is easy. You can code it up in MATLAB with the polynomial chaos expansion. And so I'll just demonstrate this to you with a simple example. So imagine that in this scenario, now we're not on the 0, 1 line, we're on the unit square. So this has never been done before. So Shavitz and Fader and everyone else basically focused on the real line. Now we want to be in an arbitrary dimension. You want to be on a sphere. You want to be in any type of dimension. How do you sort of do this stuff? So the idea, if we remember that W21 is the message point, okay? Suppose I'm trying to zoom in right here on Claude Shannon's chin, right? And so this is what W21 is, right? And then what I'm going to do is what you're going to present to me is feedback, which is this whole picture right here. And you're going to have these little grids on here. And basically what you're telling me is that, just like in the 20 questions, if it's in this quadrant, I want you to think X being, 2. If it's in this quadrant, I want you to think X is 1. If it's in this quadrant, X is 3. And if this quadrant, X is 4. So the mapping from W20 to X is given by just these 4 little quadrants right here. And so the key thing that we don't know how to do is how do I redraw the map after I've gotten an observation now, right? So that we're zooming in. And that's what building that S map is doing. So the name of the game is building this S map. And what you see, what happens in some sense is that we zoom in on parts of Shannon's face and we zoom out on others. Right? And you see the effect that we're in some sense zooming in on his chin, right? So everything that we were doing before, indirectly underneath it is equivalently this mathematics. We're kind of zooming in on some parts of the picture and zooming out on others. Okay, and this is just demonstrating that you can code it up and you can do it. And so it turns out, I won't go into this I don't have time, but using the same sort of machinery of the ergodicity and all that, along with some stuff from Lyapunov exponents, what we can show is that if any situation where the posterior belief has a density, right, with respect to the Lebesgue measure, if it's smooth, then it still boils down to asking the question ergodicity. All right, so whether or not you can even achieve any rate, if you can zoom in at the optimal Shannon theoretic speed, so I'm not just saying will it zoom in, but will it zoom in as fast as possible, that still basically boils down to whether or not ergodicity holds, right? And so, so with this, what we now start to look at is we can start to see these, these articles by like The Economist and whatnot, where they said things like put your thinking cap on, things that we used to think were science fiction are now fast becoming a reality. And the last part of my talk, what I'll just briefly go over, is the last thing that we're doing in our lab. It's not as much of the math, but this is a great article, and I really enjoyed this because it validated some of the things that we were doing. But we hate this picture, right? I don't like wearing this big, clunky EEG cap. This is interesting for a lab, but can I ever get to a point where I could do something in a coffee shop? Fine, I'm not going to fly an airplane in a coffee shop, but what if I can do other fun things with my brain signals, right? This is very limiting. So what we want to do next is we want to take, so what we've done so far, hopefully you buy, is we've taken neuroscience and applied math to throw these together. But what if we can also build better sensors, right? Unobtrusive sensors. Then we can build even more sophisticated types of paintings, right? And so the high level idea is that I was lucky to be at Illinois because, so the high level idea, if you think about it, is biology is soft, curvilinear and elastic, but the building blocks of semiconductor, of electronics are semiconductor wafers, which are rigid, planar, and brittle. And it turns out that you can develop a solution to this, and John Rogers at the University of Illinois had begun to explore a way to build flexible electronics by taking a thin layer of silicon and taking it off the wafer and mounting it onto something bendable. And so he and I teamed up to explore taking this framework to do it for the skin. So now we can make very small sensors and put them on the skin. And what we're able to build are systems that we call epidermal electronics that can be compressed and stretched naturally with the skin. And you can even embed them inside of temporary tattoos. And so here's a picture of a temporary tattoo. We put the electronics underneath it. You can integrate it onto the skin, and it can deform naturally with the skin, right? So it's kind of fun because now you don't feel it on your body because it's so thin and no one can see it, right? And so if you take a look at its capabilities, you can put a wireless antenna on it. You can deliver power to it wirelessly, the same way the Google Android phones work with NFC. You can put LEDs on here for communication purposes, or if you put LEDs and light sensors, you can sense blood oxygenation, you can monitor mechanics, you can sense skin temperature, and you can monitor the electrical rhythms of the body. And so if we focus on what we were able to do in the original paper that we wrote on this, it was very, very high level stuff as it relates to brain signals. We basically demonstrated we can pick up on like eye open and eye close in changes in your brain patterns, right? So here, eyes open, you can see more of the alpha rhythm, and eyes closed, you don't see it anymore. And so we went one step further when I got to UCSD to really test how do they compare to traditional EEG. So what you see on the left hemisphere of my head are standard EEG electrodes, and the right hemisphere, the epidermal electronics. We fed them into the exact same EEG system to test the quality of the signals, and we gave this to a certified neurologist. And you see the blue stuff and the red stuff. There's not really a difference. And so what this means in some sense is that by also building better sensors, integrating that with the applied math and the neuroscience, we're beginning to build better paintings. But what we really want to do is to really integrate these better to really do something interesting, because what I demonstrated so far is fine. You can slap a tattoo on your head, you can monitor brain signals. And so this is the most recent work that we're about to publish now, and this really is now brain-computer interface. So what we did, so in the science paper that we had, we were kind of cheating because we put one sensor here. We had to put sensors back here. I know Bruce can appreciate this. So we had a mastoid configuration. So it's not that cool because you still got to have wires going to the back of your head, etc. What we've engineered now is a system where all of the electrodes are frontal. So it's just something on your forehead. It's literally just a Band-Aid you slap on your forehead. And moreover, we haven't just demonstrated that we can pick up eye open and eye closed, but now we can really probe cognition. So what we can do is we can flash images in front of you and flash things that are unfamiliar to you and compare that to something that's familiar to you. And we'll see a modulation in your brain response, all frontal. And one of the points I want to make right here is that this is known neurophysiological results for decades. Right, if you take a look at the shape of this and the time of this, etc., this is known stuff. The only thing that we're doing differently is rather than having a whole EEG cap, we've optimized the position of the electrodes so that it's just on your forehead. And so what we like about this is that now this is really becoming a brain-computer interface that's completely sort of ubiquitous. And we have ongoing projects with connecting this to education as well as entertainment, etc. I won't be able to go into that. But in some sense, if we take a look at where we were with this picture in the Economist article that we didn't like, what really excites us now is we could imagine, what if this was the picture in the Economist, right? And if instead it was something that's more minimal, and now you can imagine potentially using this stuff in a coffee shop or something like that. So that's kind of the story.
You think you can
Miro, go ahead.
fit in the oscillators here?
Say it again.
You can fit in the oscillators here too?
I won't go into this, but well, just tell you at a high level, right? You know, there's interesting challenges here when you want to communicate on a system like this that can bend with your skin, right? So one of the things we're working on right now is we're trying to build RF antennas, right? So the resonant frequency of this thing is 2.4 gigahertz, irrespective of mechanical deformation. So this is fascinating from my perspective because at double E's, we typically think that the antenna is on some flat surface, stuff is not bending. So all the engineering you do as an EMAG person, right, is somewhat trivial. But now we want to have another robustness criterion where even when your skin naturally bends, I want that resonant frequency to always be at, let's say, 2.4 gigahertz, right? So one of the things we're doing with John Rogers is we're trying to optimize that and beat the hell out of that. But another way to think about this, maybe I don't need an antenna. Is there a different way I can communicate? So we also have an optical approach where we're using LEDs to communicate. And it's robust, and it's a much simpler circuit. It takes up less surface area, et cetera, et cetera. And the oscillators play a role there.
Stick on, does it?
Do we need to go?
How long does this?
You can wear it for about, so you can wear it, so one thing to remember is that your skin itself is an organ, right? So it naturally has a process to keep it in equilibrium. It sheds off dead skin and all that. And the process whereby it does that is about 2 weeks. So we can mount it onto your body like on a temporary tattoo. And then if you go to Walgreens and you apply a spray-on Band-Aid, then it'll laminate the sensor and you can go swimming in it and you can wear it in the shower. So it's for about a week and a half. But after that, you have to allow the dead skin to get off because this, the skin is an organ. You have to remember that. Yeah. Muriel, did you have a question?
I was just wondering about the resolution of, so I remember the earlier stuff on this kind of thing where people were doing blind source separation, right? So usually.
For EEG stuff.
Yeah, so rather than linear, they would have to go multiply numbers versus.
Exactly. So typically, right, when you have a whole, so I guess I want to be careful here, right? I want to, if you notice, we're only picking up signals from the forehead, right? So we fundamentally have a different number of microphones than if you had a whole EEG cap on your head, right? You can pick up a more sophisticated aspects of conversations, right? So the reason we want to do this is because we want to get this to a point you can wear it in a coffee shop where anybody could wear it, right? So we don't want it over the head, over the hair or anything, right? So there is a downside there, but what we do is we exploit. So my collaborator, Ricardo Gil da Costa at the Salk Institute, is an expert cognitive neuroscientist. We know a lot about neurophysiology. And what ends up happening is that even though you're right, there are these different spatial patterns and whatnot, if you're careful at what you do from an electromagnetic perspective with where you put the reference in the ground, and you know about how these distribute, you will have correlations. You'll have frontal, these networks, when they interact, there will be frontal changes that take place. So if you're careful with how you do things, you can pick it up all frontally.
I guess that's what I was asking. Right?
Yeah.
It's confounding because it seems like even with those full elements, people were getting huge amounts of noise, right?
So a great point. So the issue of movement artifacts and muscle artifacts will always be there. But one thing I'll say is that, we've made this more and more in a real-time environment. We had some guys at Hollywood come. We just slapped it on the guys. We didn't tell them anything. We just ran the paradigm, and we got these beautiful signals where the black and red differentiate very clearly. So I think you're right. Like if you're running or something, or this or that. But in a lot of situations, you'll be sitting in front of your smartphone, or you're sitting in front of your, your iPad. You're not moving that much, right? So.
The electromagnetic field you're trying to measure, it's a very mild field.
Right. So we do. There's an EEG amplifier here. So I'm sorry if I didn't make that clear. There is a high-grade, high common mode rejection ratio EEG amplifier. You do have to have all that stuff, right? Because the EEG, the brainwave signals are about 1 million times smaller than the voltage over a AA battery, right? So they're very small signals. So you need a very high common mode rejection ratio circuit, but Texas Instruments builds thin chips for that now, et cetera, et cetera. So, Muriel, yeah.
So, if you have delay in the feedback or the feedback's not so good, do you have a good idea?
So the way that we're engineering the feedback is very discrete time oriented. We literally flash an image in front of you, and then we look at that time, and then we don't make a decision. So it's very, very discrete time. We're not operating in continuous time. It's very much a discrete time system where we make this time 0, flash you something, watch the brain response for a certain number of milliseconds, right? We know how long it takes for your brain to integrate information. The cognitive neuroscience is all for the flying. We also made that discrete time. So what we did, sorry I didn't make that clear. So yeah, there's always things you don't talk about, right? But what we did is we basically use an asynchronous classifier at the level of time step I, right? So if you remember there's time step I, going from time I to I plus 1, that's not always 100 milliseconds or this or that. We use an asynchronous classifier until our posterior belief got sufficiently, right? And then we operate in discrete time. So then, yeah, so you're right. Otherwise, there'll be challenges. Yeah. Bruce?
It's something the monkey control.
Yes.
Not only its position, but input or velocity.
Yes.
any thoughts on whether that could be integrated?
Absolutely. So we had an expositor. We had a paper called Team Decision Theory and Brain-Machine Interfaces, where what we're doing right here is a special case of a more general framework of basically decentralized control and team decision theory. And you can do much more sophisticated things. It doesn't have to be just position. It could be a variety of different things. And there are nice frameworks on statistical properties between the signals that need to be obeyed to be optimal. So we talked about that, and I can give an example for this, for you can do control with both richer kinematics like speed or momentum, exactly. So we have it. I can forward you the paper. But I think this philosophical framework very much can include that. Yeah.
Well, yeah. Let's thank Todd once again.
Thank you.